All right, everyone, welcome to another video on deep learning. This one's going to be about LSTMs, and today we're going to keep it under 15 minutes. Basically, this is an extension of the video from the on recurrent neural networks, where we discussed a new architecture for processing series data and sequence data, and kind of incorporating this idea of memory into our neural network. So LSTMs, as we saw, actually, I'll dive in real quick and get into what we discussed in the last video on the architecture of our recurrent neural network. If we saw on the left right here, we see that this recurrent neural network, all it does is add an extra loop function. So instead of just having an input and mapping to an output, we map to an output, but we also pass that information from our hidden state, our hidden layer, into another time step and pass it back to the hidden layer into the new time step. And so we pass it back and it's called a hidden state. And so we end up with these kind of time steps, these steps through time where we're passing an input and getting an output. And this allows us to process sequence data. Now, unfortunately, and we're going to get into the problems of that right now, just to recap, in order to discuss the problems of that, I brought back the equation for finding the gradient of the loss function with respect to the weight parameter. And this W parameter is the one that is on the hidden state right here. So that's just one of them. There's three parameters, W, U, and V. And you can see U and V. I'm just choosing W because it has a nice long expression. But you can see there's two summation functions. One's nested inside the other. And we also have a nested pi product function as well. So, what this is going to be leading to, if you can't already see it, is multiplying gradients times each other. And there's going to be a lot of gradients being multiplied by each other as the number of time steps grows. And so, as you might have seen, as we discussed, many deep learning problems, if we're reading paragraphs or longer sequences of time series data, we're going to have a lot of time steps. And so we need something that can scale reasonably well. And unfortunately, with the plain vanilla recurrent neural network architecture, this chaining together of gradients leads to vanishing, exploding gradients very, very quickly. And so you're going to get poor results if you just stick with this basic architecture. And so that's what we're going to be discussing today. We're introducing LSTMs as a solution to this vanishing, exploding gradient problem, as well as the problem of, that's kind of a byproduct of this vanishing gradient, is not being able to remember longer context. So, as the gradient approaches, or the, gradient descent, we stop learning, we're not able to remember longer context. The information from, h of 0, if we have 20 time steps, is going to be forgotten very quickly as those later gradients take precedence on the learning of the final output. And so we're going to be solving that today with LSTMs. We're going to see how those LSTMs and GRUs solve this problem of information being lost and, of course, vanishing gradients and exploding gradients. And so right before we jump into exactly what an LSTM is, I want to contrast the three architectures, RNN, LSTM, and GRU. So on the left here, we have a plain vanilla RNN. All this is doing is this is basically just another way to represent that loop through the neural network. We're passing our input. We're adding in our hidden state from the previous hidden state, ht-1. And this is ht, let me just draw this out, ht-1. And then we pass it through a fully connected layer, followed by a tanh activation function. This is going to be a fully connected layer. A fully connected layer followed by a tanh activation function, which then provides an output as well as hidden state for the next layer. Apologies, that should just be h of t. And so this is pretty simple, but we can take a look at the LSTM and the GRU, and what they've done is actually added a lot of logic gates in this intermediary step so that we're no longer just passing our hidden state and our input and getting an output after passing through one fully connected layer. In fact, here we have 4 fully connected layers. Each of these is a fully connected layer right here. This one, this one, this one, and then this one. And we also have added, in the LSTM at least, we've added something called C of t, which is going to be called our cell state. So this is going to be CT-1. This is going to be called the cell state. So we've added an entirely new medium for transmitting information. in addition to having the hidden state. In the GRU, as we'll see after the LSTM, it's a little bit more modern version of the LSTM. The LSTM came about in, I believe, 1997, and the GRU came about in about 2014, not 2004. 2014. So much more recent. It's a little bit simplified of an architecture, but just because this one's more modern, actually, you might be asking yourself, why does everyone just use GRUs? And in fact, the answer is no. What you're going to see is there's two different approaches. They both have excellent results, but one might be better than another for different applications. So most people end up testing both of these to see which one works better. So before kind of diving into too many more details, let's dive in and see how an LSTM works and kind of break it down so you can see that it's actually not as complicated as it looks. So on the left-hand side here, we have our LSTM architecture from that we saw above. And kind of just recapping, the benefits of an LSTM, what it does is it solves that vanishing gradient problem by creating this cell state, which we're seeing C of t minus 1 and C of t. And the cell state is actually functioning as this highway for gradients and information to be shared freely across the time steps, unadulterated by fully connected layers. And I want to emphasize this unadulterated by fully connected layers here, because as you can see, the hidden state here, and the hidden state being, if we look at this hidden state, h of t minus 1, then we can see that it passes through these fully connected layers. Each one of these yellow boxes represents a fully connected layer. And these fully connected layers are passing it through a set of weights and obviously modifying it with those weights. And each of these fully connected layers has a gradient associated with this. If we look at the cell state in contrast, there is no gradient, or there's no fully connected layers interrupting the flow of information in this cell state. And that also means there's no gradients associated in modifying information here. So when we're doing backpropagation, we do not, the information that's flowing through here doesn't get lost and gets transmitted across time steps without being adulterated by these different gradients. So that's not enough on that right now. We'll get into that in a second, and it'll make more sense as we dive into the math. But just to kind of show the benefit of that having that cell state freely transmitting information is that the information from the past is remembered more easily, and the LSTMs can actually remember much longer contexts without forgetting information. So just to also kind of recap on our inputs and outputs, we have three inputs: the cell state, the hidden state, and the input, the current input here. And these are the cell state from the previous cell and the hidden state from the previous time step. And then our outputs are just the cell state, the current cell state, and the current hidden state. And this would be the hidden state that is going to the output, essentially. So, and I would, I called this O of t. This is h of t going to be O of t. Okay, so now I want to kind of break down this architecture of the LSTM. And the best way to break it down is three parts. The LSTM basically has three main gates. Even though you see kind of 4 connected networks here, we're going to see there's actually just 3 gates. And the first gate is this forget gate, which I've circled in red right here. The forget gate, and I can highlight it, the forget gate takes in these 2 vectors. What it's doing here is concatenating at that intersection. It's concatenating the 2 vectors and sending it through a fully connected layer, after which it's passed through a sigmoid function, and then it's multiplied element-wise by the previous cell state. And you might be asking yourself, what does all this mean? Let's dive into it. So first, we have this concatenation. The concatenation, it's not actually an addition function. What it's doing is let's say we have n rows, and I'll get into dimensions in a second, but later in the video. But we have the hidden state from the previous hidden state. Let's say it's n rows, and we have our input vector that is m rows. So this is n, and m. We're going to be having a resultant vector being n plus m rows to feed that into the forget gate. And then we're passing this vector of n plus m rows into a fully connected layer and through a sigmoid function. Now the sigmoid function, if you remember, it is basically mapping all these values. Let's just see an example right here. Step 1, we're mapping all those values from the n plus m vector and mapping into a vector of almost zeros and ones, something values that are going to be likely very close to 0 and 1. And so what this is going to be doing is as we multiply, then as we take this resultant vector that has a lot of zeros and ones, we're going to multiply it element-wise by the previous cell state. And so, obviously multiplying something by 0 is 0, and multiplying something by 1 is basically itself. And that's basically going to cause the values from the previous, certain values from the previous cell state. Anything that's multiplied by 0 is going to be forgotten, and anything that's multiplied by 1 is going to be remembered. So this forget gate here is basically controlling what this previous cell state remembers. And that's about it. It's literally just multiplying by zeros and ones to say, okay, which features do we remember and what do we forget? So it's that gatekeeper of what information gets remembered across the time steps. That's as simple as the forget gate. Now, the next one is going to be the input gate. So the input gate basically answers the question of what should the cell state learn from this time step. So if the forget gate was telling this LSTM what it should forget from the previous time step, the input gate is telling us what should we learn from this time step. So the input gate, and I'm going to highlight the path here, is basically taking that concatenation, passing it through a identical forget gate here, and then multiplying it element-wise by a tanh output, and I'll discuss what that means in a second. And then we're going to add that output into the cell state, which is basically going to tell the cell state what it should learn from the new information that we've passed in. So going through the process, we're passing a forget gate, which is identical to the first forget gate. And you're probably asking yourself at this point, why use two separate forget gates if they're identical? Well, the answer here is that in practice, it's been better to keep those two forget gates separate. So to keep the information that you're inputting and forgetting separate from the information that you're just telling the cell state to forget immediately. But if you look at this in theory, they are identical gates. The second step is going to be to take the concatenated previous hidden state with the current input and pass that through a tanh function. The tanh function squeezes all these values between -1 and 1. And what this is doing is essentially telling us, okay, which features are less important and do we need to actually have less of or give less importance to and reduce in value, and which features do we have to enhance in value. So I'll get into that in a second. But basically, the next step is we're going to be taking using this forget output of zeros and ones and multiplying it element-wise by these values between -1 and 1 from that tanh output. And this is going to basically just say, okay, what values from the hidden state and the current state do we have to forget as well when we are learning, what's important again. And so the output of that is going to just be a bunch of features that are either negative or positive. And obviously some features are going to be 0 as well because we're going to have forgotten them. But then we're going to add those element-wise to the cell state. And so what this is going to be doing here is that the elements that we want that are important are going to be increased in value, and the elements that are negative, it's going to decrease those features in value. It's going to decrease the value of those features. So let's take this step back and look at an example of this. Basically, let's say if we were taking a problem reading a paragraph about elections, the presidential election or something, and we had a bunch of words, and the words like the or unimportant words would probably just be forgotten by the forget gate. But then there's words that may be slightly irrelevant, like people or chose or even just presidential. Those type of words, maybe they're slightly relevant for context, but they're not as relevant as the words like selected and, voters and choice. Things that, maybe this might not be the best example, but there's certain words that are much more relevant to helping us understand the context of the article and maybe even the outcome of the election or whatever it is. And those are going to be enhanced in value. Whereas the words that may be redundant or maybe not offering enough information one way or the other to help us figure out the context of the article, they're going to be reduced in value and reduced in importance. So the result of all this is that the cell state is updated with the new features that the model considers important. That's about it. We're just telling it what should we learn now. So that brings us to the third part, which is the output gate here. The third part, the output gate, and I'll highlight this, has another forget gate as well. And all this is doing is taking the information that we've learned in the cell state and using it to create to tell us what should we pass in our next hidden state, right? So the output gate really is just finalizing the information of the hidden state and telling us what we're going to pass on to the next time step. And the output gate has three main steps. We have an identical forget gate that tells us what information from the previous hidden state and the input we should forget, and then multiplies that element-wise by the importance by the output of the tanh function from the current cell state, and that's basically going to just give us a hidden state that has the right things to remember and forget. And then also, of course, the tanh function assigns a weight of importance to the either negative or positive to the cell state features, and so we're going to get the right features to be passing on, and whether they're relevant or less relevant. So the result is that a hidden state has a lot of features which have either been forgotten or enhanced by the current cell. So moving on, just to kind of summarize, summary intuition here, we have three gates: forget, input, and output. The forget gate tells us what information we should forget and remember. The input gate tells us what from the previous time step. The input gate tells us what information we should learn in the current time step, and the output gate is telling us what information we should be passing on into future time steps. And just to kind of reiterate this, if it wasn't already clear, each yellow box here is with either sigmoid or tan is representing a fully connected network with trainable weights and parameters. And that is the key distinction in LSTM, is that cell state has no fully connected networks, whereas the hidden state does. And so, but in reality too, while the cell state benefits from freely flowing information, the hidden state and the fully connected networks are truly what learn, what to remember, and what to forget. So they are a essential part of the network here. And the key is to note, well, I already actually mentioned it. Of course, we're noting that, that cell state doesn't pass through any fully connected layers, and that's what makes this able to pass information very easily throughout time. Doing a little bit of dimensional analysis real quick, like I mentioned before, we have, just to calculate the number of parameters that we're going to have to be training, just so you understand. It's very important to look at the dimensions when you're doing this type of stuff. But basically, we're passing in the cell state and the hidden state from the previous time step. They're both going to have the same dimension. We're going to call it n. Then we're going to pass in our current input. It can have any dimension, which we're going to call m. We're going to concatenate these two to have a vector of n plus m rows in one column. And then we're going to pass that n plus n row vector through the fully connected layer and kind of squeeze it into a resultant n row vector that will be passed to the rest of the network. If you look at this LSTM network, all of the vectors have the same number of rows, except for that initial concatenation, and all the fully connected layers take care of that dimensional reduction. And to look at the number of parameters, all we do is take the number of output neurons in the fully connected layer and the number of input neurons and multiply them by each other, and then add on, of course, bias for each of the output neurons. So that'll be n plus n times n plus n. And we get mn plus n squared plus n. And then we have 4 fully connected layers here, so we're going to take that entire expression, and multiply it by 4 to get this expression here. And as you can see, I wanted to do this dimensional analysis to kind of show you how this is actually a lot of parameters to be training for one single state. And it turns out that, LSTMs, while we do get much better results in learning and we don't have that problem with exploding gradients, we do have a much more computationally expensive and memory intensive operation going on here. So that is something to keep in mind, that, we are getting better accuracy, we're getting something that's more robust, but at the expense of being a lot more computationally expensive and, of course, allocating more memory. And that brings us to our next video, in which we're going to talk about a computationally cheaper alternative. That's the GRU, and I saved it to be after the LSTM because it is this known as kind of, okay, it's a little bit more lightweight and efficient version of the LSTM. Now, it's not necessarily better than the LSTM, so I want to make sure to emphasize that it's not necessarily better. There's many applications where the LSTM performs better and many applications where GRU performs better. But I do introduce it after the LSTM because it is a little bit more simplified in architecture. It has 2 gates instead of 3, and it's a little bit more efficient computationally. And that's mainly because if we're looking at it, there's only 3 connected layers here, and we're able to get away with that because we don't have a cell state. We're just passing everything through the hidden state and using this type of alternative logic to modify the hidden state in a way that enables it to not pass through all these gates necessarily, right? It doesn't have to pass through fully connected layers, and therefore doesn't necessarily get adulterated by the gradients, and so we can still have that long short-term memory. Lastly, I actually just realized I didn't talk about why it's called long short-term memory. It's called long short-term memory because in each state here, we're using short-term memory operations to figure out what we should remember in the long term and have a long-term memory. So just remember that, and it'll help you understand intuitively what we're doing here with whether it's a GRU or whether it's an LSTM. So that's it for this video. Stay tuned for more content, and I will see you